This is the next question. It says in the figure 2115, a central particle of charge negative q, this is this particle, is surrounded by two circular rings of charge particles. What are the magnitude and direction of the net electrostatic force on the central particle due to the other particles? So what do you think? You can give a simple expression.
Would it be 2kq squared over r squared up? No, or down? Up.
Up is correct, yes,
Yeah.
very good. Yeah, you see that for each one of these particles, there's one exactly in opposite position. So the force of this one and force of this one cancel on that. Force of these two cancel. All of them are symmetrical. So all the forces cancel. The only one that is not canceled is this one. So it becomes k times 2q times q divided by this lowercase r squared, because that's the distance between them. And it is up because it is attractive, and one is negative q, one is positive 2q. So they attract each other. So the force on the central particle will be up. The force on this one, of course, will be down due to that one. Okay? Does it make sense? Any questions?
Wait, can you repeat the answer again?
All of these have symmetry, so they all cancel each other. You see this one with this one cancels. This one cancels with this one. This one cancels with this one. The only one that doesn't cancel is this. And this is charge Q negative. This is 2Q. So the F net will be K times 2Q times Q divided by R squared. You see the distance is R, right? And so it is 2kq squared over r squared, and at the direction up. Up because this one gets attracted to the opposite charge. Does it make sense?
Yeah, thank you.
You're welcome. All right. Any questions about this?
I have a question. Does like the sign of the cues matter in this case?
That's right. The sign, yes. For example, if you look at this one and this one, both of them repel this central charge, right? So this one applies a force like that. This one applies a force like that. They both repel them. But in terms of the final answer, because this one is negative q and this one is positive, it's attractive. So the force on the central particle will be means toward that, right? Remember we said that the force is toward the other particle if the charges are opposite, and is away from that other particle if the charges are the same.
All right, thank you.
You're welcome. Any other questions? All right. So let's go to the next one. Here it says that the figure shows three situations involving a charged particle and a uniformly charged spherical shell. The charges are given and the radii of the shells are indicated. Rank the situations according to the magnitude of the force on the particle due to the presence of the shell, greatest first. You have situation A, B, C. You have the particles Q, positive 2Q, and 6Q, and the shells have 5Q, negative 4Q, and 8Q. You want to see which one has more forces on the particle. Rank the situations according to the magnitude of the force on the particle due to the presence of the shell. Greatest first. What do you think?
Well, we know that A would have a 0 net force, right? Because it's inside of the shell.
That's right. The f of A is 0 because shell theorem says that when a particle, charged particle, is inside a charged shell, there's no force acting on the particle from the shell. What about the other two? This is tricky because the shell theorem says that no matter what the radius of the shell is, as long as the charged particle is outside the shell acts like a particle at its center, right? So it means that in part B, you can put all of these charged negative 4q of the shell at its center. And it's like two particles like this attracting each other. And in part C, is all the 8q of the shell will be also at its center, right? So it doesn't matter what the radius of shell is, as long as the particle is outside, we can use the shell theorem, right? So now, which one is greater? Here, now we can treat them as particles, right? So we can say FB is K times 2Q times 4Q. You say that it's absolute value, so we don't write the negative. Divide by this D, the distance between the center to the particle, D squared. Right? Is that clear? And FC is K times Q times 8Q. Divide by the distance again is D. These two the same?
Yeah, they're the same.
Yeah, they are the same. So FB is the same as FC and is greater than FA. So the answer is FB is equal to FC greater than FA, which is 0. Does it make sense? Any questions? So you see that the thing is that the radius of the shell doesn't matter. The shell theorem says that as long as the particle is outside, you can put all the charges of the shell inside at its center and consider the particle. So that makes this shell and this shell effectively having the same force on these two. Of course, the multiplication of charges apply here. 2 times 4 is the same as 8. 1 times 8. So they make the forces the same. Any questions? Okay, so we'll go to next. So here is a general thing. You see, if you have an arrangement of the charges, like these 2 positive Qs and 2 negative Qs, and they are at different positions at the corners of a rectangle, you want to see what is the net force acting on this corner charge due to all other 3. The steps are this. First, focus only on that charge. If you want to calculate the net force on this top right corner charge, just focus on that. Don't worry about the forces acting on the other charges. Focus on the forces acting on that charge. And then draw individual forces on that charge due to each of the other charges and choose a name for each force. For example, say this one applies this force. This one applies this force, I call it F1. And this charge applies this force F3. This should be F3. All right, so there are three forces from each one directly away or directly toward, depending on whether they are the same sign charges or opposite sign charges. For example, the top two, they both are positive, so they repel each other. But the forces due to the other two, the lower charges, because they are negative and that charge is positive, this is positive, this is negative. So the force is toward that. And this is also positive, this is negative. So this force is toward. Draw the individual forces either toward or away from each charge directly. All right? And then imagine a coordinate system set up with its origin at the position of the charge. So like at X and Y here, but written, drawn from this point, drawn from the charge Q, right? And then split each force into its component in that coordinate system. So each one of these forces in the coordinate system has two components. You just split them and add all the X components to find the X component of the net force. We call it F net X. And add all the Y components to find the Y component of the net force, which we call F net Y. And then find the magnitude of the net force by this formula. F net magnitude is equal to X component squared plus 1 Y component squared under square root. You know these formulas. And the direction of the net force on that charge from positive direction, positive X direction counterclockwise is theta tan inverse of Y component over X component. And then make sure to add 180 degrees to theta if the X component is negative. To find the correct direction if the net force happens to be in the second quarter or third quarter. You know that when you want to calculate the angle, you use tan inverse of Y component over X component. No matter what value of Fy over Fx is, the tan inverse only gives you values between negative 90 degrees to 90 degrees. So those are only in the first and fourth quarter. It never gives you a value like this. It never gives you the angle in these quarters. In order to get that, you need to add 180 degrees to the value of theta you get from this formula. Okay, so you put F net X and F net Y with their signs, whatever they are, and calculate tan inverse. That gives you an angle. That angle is always between negative 90 degrees to 90 degrees. If F net X or if X component is positive, that is exactly the directional angle. If it is negative, it is the wrong directional angle. You have to add 180 to the value of theta that you get, then you get the right angle, the correct angle, okay? All right. So now, as an example, I'm going to calculate force on this one, on the lower right corner charge. All right, so let's do that. Okay, if I want to calculate the force on this one, this has three forces on it from all the three other charges. First, this one, which is at the lower, I should call them 1, 2, 3. Let's call this 1, 2, 3. The force of 1 on this negative Q is attractive. Means on negative, I'm concentrating on this negative Q, okay? So what is the force on that due to the one on at the top? Say, okay, that force is attractive, so it's directly upward, right? And then what is the force of 2 on that? This is a repulsive force because both of them are negative. So on this negative Q on the right, it would be to the right because it's away from the other one. So this is F1, this is F2, and F3 is along this line that's connected to the two charges, and one is positive, one is negative, therefore it is attractive. So on this negative Q, the force will be toward the other one. So that's F3, right? So these are the directional forces, but the magnitudes I need to find. I use the Coulomb's law to find the forces, the magnitude of the forces. So F1 is K Q times Q. We don't put the negative sign because it's absolute value. So Q squared over A squared. So it becomes 9 times 10 to the 9 times Q is 2 times 10 to the negative 5th, right? 20 times 10 to the negative 6. So 2 times 10 to the negative 5th squared divided by A squared. A is 20 centimeter, right? Because B is 30 and it's 1.5 A. So it's 20 centimeter, 0.2 meters squared. So if I calculate that, comes 90 Newton. Okay. And F2 will be K, again, Q squared divided by B squared, right? So it becomes 9 times 10 to the 9 times 2 times 10 to the negative 5th squared divided by 0.3 squared. That's B in meters. So this 3 squared with 9 cancels. And then you get, again, 4 times 10 to the first. So it becomes 40 Newton. And then F3 is KQ squared again, divided by A squared plus B squared. This is R, the distance between them. R squared is equal to A squared plus B squared, right? This is R squared. So becomes again 9 times 10 to the 9 times 4 times 10 to the negative 10 divided by 0.3 squared plus 0.2 squared. So if you calculate that, it will be, I think, 27.7, was it? Newton. All right. And now we have all these three magnitude of the forces. This F1 is in the Y direction, F2 is in the X direction, but F3 has an angle. Let's call it alpha. I don't call it theta because I want to reserve theta for the net force, okay? So what is alpha? We can use tan inverse of A over B, right? Or tan inverse of B is 1.5A, so 1 over 1.5. If you do that, you get, how much will I get? 37.7? Yes. At 37.7 degrees. Now that we have alpha, we can have all these components very easily. So what is F net X? F net X is sum of all the X components. F1 doesn't have X component. F2 has the X component the same as its magnitude. And F3 has X component that's negative, and it is magnitude of F3 times cosine of alpha. Right?
Professor,
Yes, please.
I think I calculate alpha wrong. Is supposed to be 33.7.
Yeah, I thought so. 33.7, I think that's correct. Thank you. And F net y is all the y components, which is f1, it is all in the y direction, plus f3 times sine of alpha. Is this clear? You're adding the x components. So now you have these values you can put for fx. So f net x is f2, which is 40, minus f3, which is 27.7, times cosine of 33.7. And what does it come to? And f net y is f1, which is 90, plus 27.7 sine of 33.7. So once you get that, you can have these two, then you find the magnitude and direction. I have these calculated. Let's review that. The rest is easy, but let's review everything. So this is f1, f2, and f3 is in this direction, like that. Alpha, f1 is kq squared over a squared. That's the value, 90. f2 is kq squared over b squared, which becomes 40. f3 is kq squared over r squared, which is this 27.7. All right? And then f net x is f2 minus f3 cosine alpha, f net y f1 plus f3 sine alpha. Alpha is tan inverse of a over b, which is 33.69. F net x is 40 minus 27.7 cosine, becomes 16.96. F net y is 90 plus 27.7 sine 33.69, 105.36. And then F net becomes sum of the square of the components, turns out to be 106.7. Theta is tan inverse of F net y over F net x, but F net x is positive, so we don't need to add 180. Tan inverse of 105.636 divided by 16.96 becomes 80.9 degrees. So F net is this magnitude at this direction. So this is the answer. All right? And when you draw it, it becomes like that. This F net is sum of all those three. Any questions?
I do, Professor. Yeah. And when you said that you don't have to add 180 degrees to the theta, why is that again?
Because the x component, this is positive. You see, this is positive. Means that, you see, the x component is positive, means it is in the first or fourth quadrant. And when it is in that case, this tan inverse of y component over x component gives you exactly the direction. But if x is negative, means that the vector is in the second or third quarter, right? In the second and third quarter, x is negative.
Oh, okay. I understand now.
In that case, you add 180 degrees to what you find here.
Okay. Thank you, Professor.
For example, it is a very good question. You see, for example, if both of these were negative, means if both x component and y component were negative, or x component was negative 16.96 and y component was negative 105.36. The tan inverse would be, you know, negative over negative becomes positive, would be exactly that, right? Do you get that? If both of them were negative, the negative would cancel. You would get exactly 80.9. But if both of them are negative, then the vector is in the third quadrant, right?
Right.
And then if you add 180 degrees to this, you get exactly that direction.
Okay, I understand now, Professor.
You're welcome. All right, and also if one of them is positive, one of them is negative, the tan inverse becomes a negative value. But if the y is negative and x is positive, that is in the fourth quadrant where it should be, right? But if it's the other way around, if the x is negative and y is positive, then it is in the opposite direction. Again, what you get, if you add 180, you go to the exact correct direction. All right, so let's move on. This is another question. I tried to put a variety of examples here so that you see a variety of different kind of questions that are in the book. The book is really a good book. It has a lot of different questions, and sometimes you have to think about how to proceed to get to the answer. So it says two particles are fixed on an x-axis, like these two that you see on the x-axis. Particle 1 of charge 40 microcoulomb is at x equal to -2 centimeters. So this is particle 1. Particle 2 of charge q not given is located at 3 centimeters. So this is particle 2. Particle 3 of charge magnitude 20 microcoulomb is released from rest on the y-axis at y equal to 2 centimeters. So this is particle 3 at 2 centimeters on the y-axis and has a magnitude of charge that is 20 microcoulomb. What is the value of q? So this, if the initial acceleration of particle 3 is in the positive direction of x-axis or the positive direction of y-axis. So two cases. Part A, what is q if the initial acceleration of particle 3 is in the positive direction of the x-axis? Means the acceleration is this way. So what do you think? Any ideas? The first dots you need to connect is that acceleration is in which direction? I mean, in general, from Newton's law. See, F equals ma is a vector equation, means that whichever direction force has, F net, should say. Whichever direction F net is, the acceleration will be in that direction, because when you multiply a scalar mass times a vector, it gives you the vector that is in that same direction. All
So
right?
it go in the positive direction.
Yeah, so the net force should be in the positive x direction. So F net should be in positive x direction. And we're talking about part A. Okay? And then, okay, how do you use this information? This is very important. We have some information here, but how do we use this information to solve the problem?
Is it only in the x direction? The f net?
Yeah, F net is in the x direction, yes. So how do you use that to find the value of Q?
You would need to cancel out the, what's called, the vertical force component of the 40 of particle 1 using particle 2.
Yes, very, very good. Yes. A vector is in the x direction if it doesn't have y component. So in order to use that, so F net y should be equal to 0, right? Saying F net is in the x direction is the same as saying the y component of F net is 0. So that is the condition. You see, we need an equation. We need an equation to find a quantity, right? When you want to find a quantity, you need to write down an equation. This being in x direction without having the magnitude doesn't give you a equation. But this one is equation to write down to find Q. Okay. Now, this charge Q, should it be positive or negative? Let's say this is positive and this is also positive. Should Q be positive or negative?
Negative.
Negative. Why is it negative?
It's attractive
Yeah,
to the
attractive.
positive direction.
That's right. This one, you see, it is the motion of particle 3 that we are considering. Therefore, we should look at forces acting on particle 3, right? And if both of those are negative, then the force of 1 on 3 will be repulsive, so will be this direction. So this is F1. And then in order for the y component to cancel, this Q should be attractive so that the force is this way. Because if it is also positive, the force will be repulsive, it will be in this other direction, right? It will be in the other direction. We don't need it to be in that direction. Sorry. Okay. So this is F2. All right. So the condition to be set is the y component to be 0. So we find sum of the y component, F net y, which is F1y plus F2y should be equal to 0. Right? Okay, how do I find F1y and F2y? First, we need to find F1 and F2, right? So F1 is K Q1, Q3. We write Q1, Q3 divided by this R1, let's call it R1 squared. 9 times 10 to the 9, Q1 is 40 times 20 divided by what is R1 squared, which is 2 squared plus 2 squared. I didn't put everything in correct units because the units will cancel. All right, so 9 times 8 divided by 4 plus 4 times 8, this is 9. It's in some units. All right.
Oh,
Yes.
sorry. Why would the distance be 2 squared plus 2 squared?
These are 1 squared from the right triangle here. You see the right triangle?
Yes.
So the distance between 1 and 3
Oh, okay, I see.
are 1.
Okay, I understand.
Yeah.
Thank you.
You're welcome. All right, this is in, this will be in a weird unit, 9, but when the charges are in microcoulomb, this will give you 9 times 10 to the, oh, 8 cancels, 10 to the 11, right? And then F2 will be K, Q1, Q2, no, Q2 to Q3, because it is on 3, divided by R2 squared. R2 is here. Again, instead of R2, I put Q2, which is Q, we want to find, Q3, which is 20, divided by R2 squared, which is 2 squared plus 3 squared, right? That's 13. So that's 18. This is 2 times 9 times 10 to the 10 divided by 13, right? Cube. I mean, I think the way I'm doing it is probably confusing you, but let's see what happens. Because the units are not the standard unit. All right, this is F1 and F2, but now we want F1y and F2y to add up to 0. So you see, this is F1 magnitude times sine of 45 degrees, right? Plus F2 sine of this angle, which is the same as this angle, alpha, see? And sine of this angle, sine alpha, equal to 0, okay? Actually, the magnitude should be equal to 0, so negative here. All right, and then, so F1, now we have 9 times 10 to the 11, that's F1, as square root of 2 over 2, the sine of 45 degrees, should be equal to 18 over 13 times 10 to the 10 cube, that's F2, times sine of alpha. In sine of alpha, I can write 2 divided by square root of 2 squared plus 3 squared, which is 13. Okay, this is the equation that comes from this equation. All right, and now I can drop some of these factors. 10 to the 10 can be canceled. 90 square root of 2 over 2 equal to 18 over 13, and then square root of 13, right? And times 2 cube equal to, is there anything here I can drop a factor of 9 here, I'll make this 10, times this becomes 2. So 130 square root of 13 divided by, oh, square root of 2 times square root of 2 divided by 8, right? 2 times 2 times 2. So that's Q in micro Coulomb. What is that number?
I got 82.9.
82.9. That sounds right. 80.9. Because we have 2 sig figs, so we can say 83 micro Coulomb. All right. Therefore, Q is negative 83 micro Coulomb. So this is the answer for part A. For part B, if the acceleration is in the positive y direction, first of all, what should be the sign of Q? F1 is the same direction. In order for the x components to cancel or the net force to be in the y direction, Q should be repelling the Q3. Therefore, the y component is non-zero, the x component is 0. So Q should be positive. Part B, Q should be positive, then F net x should be equal to 0. Again, you do the same thing. Set the x component equal to 0, and you get an equation, you solve for q. Any questions? All right, this seems to be a little bit messy. I'm going to do that a little bit more neatly using algebra, because these numbers that I put here, and then at the end they cancel. And if you do it algebraically, then you see the cancellation. It becomes a lot cleaner and more understandable. So here I'm doing it again. This is F1. It just makes an angle of alpha 1. Of course, alpha 1, because these are the same, becomes 45 degrees. And alpha 2 is a different value here. So we said that we can put f net y equal to 0, which is f1y plus f2y equal to 0. So f1y becomes f1 sine alpha 1. f2y becomes negative f2 magnitude times sine of alpha 2. And that should be equal to 0, means that this should be equal to that. And now f1 has a magnitude of k q1 q3 over r1 squared times sine alpha 1 becomes equal to magnitude of f2, which is k q2 q3 over r2 squared. R2 is this distance that I didn't write here because it gets busy. This is f2 magnitude times sine alpha 2. So these two should be equal, and then you see that k cancels out, q3 cancels out. It doesn't matter what value of q3 we have. And this simplifies to this equation. And q1, r1, r2, and the angles are known. I can solve for q2. q2 becomes q1 times r2 squared over r1 squared times sine alpha 1 over sine alpha 2. Solving this equation for q2. And now we have all these values. We can just enter the numbers right now. q1 is 40 microcoulomb, so we put that. R2 squared is this one, which is hypotenuse of this right triangle, becomes 2 squared plus 3 squared in centimeters squared, because that the unit doesn't matter because they get canceled here. And R1 squared becomes 2 squared plus 2 squared. So that's R1 squared. The sine of alpha 1 is 45 degrees. So sine of 45 is the square root of 2 over 2. And sine of alpha 2 is this angle, alpha 2 and this angle are the same. Sine of this angle is opposite over hypotenuse. So it becomes 2 divided by square root of 13. So this becomes Q2. Now you see that these 2 goes in the denominator, makes a 4, but this 4 cancels out. So that becomes 10 microcoulomb times 13 over 8 times square root of 2 over 1 over square root of 13. So multiplied by square root of 26. And if you calculate all of that, becomes 83 microcoulomb. So Q2 becomes 83 microcoulomb. And also, as we said, Q2 should be negative. Therefore, Q that we were looking for is negative 83 microcoulomb. In the figure, particle 1 of charge 1 microcoulomb and particle 2 of charge negative 3 microcoulomb are held at separation L equal to 10 centimeter. If particle 3 of unknown charge Q3 is to be located such that the net electrostatic force on it, on particle 3, from particles 1 and 2 is 0, what must be the x and y coordinates of particle 3? So, first of all, what is the y coordinate? If two forces to be balancing each other, they have to be on the same line. But if the particle 3 is not on the same axis, these two forces cannot be on the same line. So the y coordinate, y should be equal to 0. That is not by calculation, it is by inspection, okay? But what about x? Assume that Q3 is at x and 0, means at on the x-axis at the position x. The forces can cancel only if they have the same magnitude and are in opposite direction, okay? here particle 1 is positive, particle 2 is negative. All right, so and negative 3 here in positive 1. Should the particle be to the left of 1 or between 1 and 2 or to the right of 2?
On the left of particle 1?
The left of particle 1. So if it is on the left side, one of them is pulling, attracting it, one of them is repelling it, and the smaller particle is closer, so it is possible to balance them. So X, from this inspection, X should be negative. It means that the particle should be in the negative X direction, negative X position, right? F on 3 due to 1 is equal to F on 3 due to 2. So this gives you this equation, KQ1 Q3 divided by X squared equals KQ2 Q3 divided by L minus X squared. L minus, whatever, one is at L, one is at X. The distance is L minus X. The other one, 1 and 3, if you look at 1 and 3, no matter where X is, the distance between 1 and 3, because 1 is at the origin, the distance is X, right? The absolute value of X. But the distance to the particle 2 is L minus X, absolute value of L minus X. So because it squares, it doesn't matter. So this is what you get, the equation that you get. Then if you cancel all the K and Q1 and put Q3 and values, you get this equation. 1 over X squared, because this Q1 is 1 microcoulomb, this is 3 microcoulomb, and microcoulomb cancels out, Q3 cancels out, and the absolute value takes care of the negative sign, right? You have 1 over X squared. On the other side, you have 3 over L minus X squared. So this is an equation that you get to solve for X, with the position of that third particle. And then you can cross multiply it like that, and then take the square root of both sides now, get L minus X equal to positive and negative square root of 3X. Remember, when you take square root of an equation, in order not to lose any solutions, you have to put positive, negative, okay? And then for positive, you get this. X becomes L divided by 1 plus the square root of 3, because X goes to the other side. You can factor X, get 1 plus the square root of 3. So X becomes L over 1 plus square root of 3. So X equal to 3.66 centimeter. For negative, you put X to the other side and factor and divide, you get X equal to L divided by 1 minus square root of 3. So X is negative 13.66 centimeter. Which one of these is acceptable?
The negative one?
The negative one, because we just talked about, in order for the third particle to be in equilibrium, the third particle should be in the to the left of particle 1, which is in negative X position. So this is the position of particle 3. So the other one is not acceptable. Okay? Of course, this is when the magnitude of the two forces are the same, but they happen to be in the same direction, so they cannot cancel each other. But in the other case, negative 13.66 centimeter, they are in opposite direction and they are the same magnitude. Okay? So this is the solution to this problem. All right? Any questions?